Hello and welcome to video 6 of Module 7. In this video, we'll be talking about some terminology surrounding something called a hypothesis test. We won't conduct any of these tests in this video, but we will talk about some of the vocab and some of the processes. And then in the next video, we'll put it all together. Now, we've been using the central limit theorem and the standard normal curve to help us do some analysis, like creating a confidence interval for population mean. This new way that we're going to use these techniques is to help us to test a claim about a population mean. Now, this type of test is called a hypothesis test, and it's going to be based off of how likely or unlikely a certain result is if that claim were to be true. So, for example, suppose you're reading in a magazine or online or something, and it says that we just did this study and we found out that the average height of men is 10 feet tall. And if you read that, you would probably say, what? That's ridiculous. Men aren't 10 feet tall, right? That's way too high. There's got to be something wrong with that. So in this case, that initial claim, men are 10 feet tall, is going to be one hypothesis. And your counter-argument or your suspicion that men are not 10 feet tall, they're shorter than that, that's going to be another hypothesis. Here's what that looks like more formally. The status quo, or the claim that you are challenging in a hypothesis test, is called the null hypothesis. So this would be the statement, men have an average height of 10 feet tall. The notation for this is an H with a subscript of a 0. We're going to call this H null or H naught or H0. Any of those are going to work. So this is our null hypothesis, and the null hypothesis is always that the mean equals some number. So, for example, in that made-up claim that men are 10 feet tall, the null hypothesis would be mu equals 10 feet. That's what it would be. The hypothesis you're using to challenge the null hypothesis is called the alternate hypothesis. So the alternate hypothesis is what you suspect might be true. And the way that you form your alternate hypothesis, we're going to choose one of three, and it will be based off of your suspicions. So in the case of men being 10 feet tall, my suspicion is that that is too big. Men are actually shorter than that. So I would choose this first form of the alternate hypothesis, the left tail, and I would have mu is less than some number. Notice that for the alternate hypothesis, we have an H1. So if 0 is the original null hypothesis, the next one is H1. Sometimes you'll see an HA for alternate, so that's another notation that is used. So a left-tailed alternate hypothesis is if you suspect the true mean to be less than the claim. If I were to make a claim that the average temperature in Utica, New York is 12 degrees in June, you would look at me funny and say that's ridiculous. The average temperature in June is much higher than 12 degrees, so you would be making a right-tailed test. So you would say that mu is larger than some number. And sometimes you might not have a suspicion in a direction. So you might not know whether the actual value is more or less. You might just think that it's not equal to, it's different from the claim. So that would be a two-tailed test. And they all basically look the same. The part that's changing is whether you use a less than, a greater than, or not equals to. A place where you might use a not equals to alternate hypothesis would be if you're trying to see if a scale is calibrated correctly, and you're not sure if it's, adding pounds or subtracting pounds. You just think it might not be weighing correctly. So you would perform a two-tailed alternate test, alternate hypothesis. So let's look at an example here. So suppose Alice, Ben, and Carol are studying changes in temperatures in the Northern Hemisphere. And Alice suspects that a global warming is occurring, and Ben thinks that it's actually a global cooling. So Alice thinks that temperatures are warmer than they used to be. Ben thinks that they're colder than they used to be. And Carol isn't really sure how the climate is changing, but she thinks it's changing somehow. So the three of these people work together to find the mean daily temperatures for 1950 and for 2010, and they record the difference between the 2010 and the 1950 daily temperatures. So, for example, they're going to take, like, if we look at, I don't know, April 15th in 2010, and they look at April 15th in 1950, and they say, what was the average temperature on April 15th for these 2 years? And then they subtract the two amounts. So if 2010 and 1950 were about the same, if the temperatures were the same, when you subtract them, you would get 0. So if temperatures are not changing, then the average difference between the two temperatures would be a 0. This is going to be our null hypothesis. So the null hypothesis is that mu equals 0. There's no change in temperature occurring. Now, Alice, Ben, and Carol think that the temperature is changing. So they are fighting a statement that it doesn't change. Okay, so that's how we're getting this null hypothesis. Now, even though all three have the same null hypothesis, they all have different alternate hypotheses because they all have different suspicions about what's going on. In the case of Alice, Alice thinks that there's a global warming. So she thinks that temperatures in 2010 are going to be higher than temperatures in 1950. So if I take a big temperature from 2010 and subtract a colder temperature from 1950, I'm going to get a positive result. So Alice's alternate hypothesis is going to be that the mean change in temperature is positive. It's bigger than 0. On the other hand, Ben thinks that there's a global cooling happening, so that temperatures in 2010 are colder than temperatures in 1950. So if you take a small number and subtract a big number, that's going to give you a negative amount. In other words, Ben is going to suspect that the mean change in temperature is a negative number. And Carol isn't sure how it's changing, but she thinks it's changing somehow. So she just thinks that it's different. So Carol's alternate hypothesis is going to be that the mu is not equal to 0. She's not sure whether it's bigger than 0 or less than 0. She just thinks it's going to be different. So even though all three people have the same data, or are going to be sharing data or whatever, or they all have the same null hypothesis, it's possible to set up a hypothesis test with different alternate hypotheses depending on what you suspect may be happening. You do want to set up your null and your alternate hypothesis before you go out and collect the data, because you don't want the data to kind of influence what you're working on. Otherwise, you'll get some kind of bias going on. Now, when you conduct a hypothesis test, at the end of the test, you're going to draw one of two types of conclusions. Either your suspicion was warranted, so you do in fact find that men are shorter than 10 feet, so you will reject the null hypothesis. So if your suspicion turns out to be true, you reject the null hypothesis. If not, if the evidence you find does not support your suspicion, then you fail to reject the null hypothesis. Now, this language is in terms of reject and fail to reject because of a certain reason. So let's look at an example to see why we might be using this kind of language. So suppose you have a collection of teddy bears. So here you have a bunch of teddy bears. And your friend makes a claim to you, and your friend says that all teddy bears have yellow fur. And you say, no, I can disprove you, my friend, because behold, in my collection of teddy bears, I have quite a few teddy bears that do not have yellow fur. I do have some, but in fact, I have a lot that don't have yellow fur. So this is where we're in that first situation where your suspicion is warranted and we reject the null hypothesis. Somebody makes a claim, all bears have yellow fur, and we reject it. We say, nope, doesn't work. Here are some cases where that's wrong. Now, suppose your friend makes a claim that all green teddy bears have to have a flower attached to them. Now, if I look at your collection, you can't disprove that because you don't have any green teddy bears, right? So if we make this claim that every single teddy bear that's green has a flower attached to it, I can't disprove that claim based on this collection that I have. I can't prove it either. It just happens that I didn't capture any green teddy bears in my sample, so I can't really make any conclusions about it. This is the case where we're in the second statement. So our evidence doesn't confirm a suspicion that there's probably a green teddy bear that doesn't have a flower. We haven't proven that all green teddy bears have a flower. We've just failed to disprove it. So that's why we use this language, fail to reject, as opposed to prove. So when you draw a conclusion, you can either reject the null hypothesis or you can fail to reject it. So an important part here is you can never prove the null hypothesis. You can only reject it or fail to reject it. And it's this type of statement that makes reporting on scientific hypothesis testing difficult, because in science you're going to come up with a theory, right, scientific idea, and you're going to test the heck out of it, and you're either going to have a rejecting of a null hypothesis or a failure to reject the null hypothesis. So you can never prove a scientific theory. Now, this doesn't mean that, you know, the theory is wrong. I mean, we use this all the time, but it makes taking the scientific language and putting it into our everyday talking a little bit of a challenge. Now, the way that we will make this decision to reject or to fail to reject is based off of something called a p-value. So we're going to do a bunch of math to find this p-value, and then once we have it, we'll compare it to a significance level. And the significance level, like with our confidence intervals, I always told you the confidence level to use. You will always know the significance level to use in a hypothesis test. And this is either a 0.01 or a 0.05. And you see that little, it kind of looks like an A, that symbol. This is the Greek letter alpha. So alpha is our significance level. If it's a 0.01, that's sometimes referred to as the 1% level, and a 0.05 is sometimes referred to as a 5% level. Basically, the significance level is a way of telling whether something is weird or not. So, for example, consider you went out and you looked at a population for a certain characteristic, and you find that 60% of the people in your group have this characteristic. Well, 60% isn't weird, right? That would mean, okay, this is a sort of typical characteristic to have. Suppose you went out and you found that only about 30% of your group had this characteristic. Well, 30% is the minority, it's less than half, but it's still pretty sizable. That's 1 out of 3 people, right? So you wouldn't consider this to be a weird characteristic either. So what we're trying to determine is, like, what is a cutoff for weirdness, right? 30 is not super weird, but what about 25%, 1 out of 4, or 10%, 1 out of 10, or 100%, 1 out of 100, right? So where is this cutoff for what we're going to call weird versus not weird? That's what the significance level is. When we use the 0.01 level of significance, we're saying that if the characteristic happens less than 1% of the time, it's weird. If we use the 0.05% level, or the 0.05, sorry, if we use alpha equals 0.05, that's the 5% level. We're saying if it happens less than 5% of the time, we're going to call it weird. And different fields of study use a different cutoff for weirdness based off of, you know, what's sort of expected or what they anticipate in their field. So, for example, the softer sciences like psychology, sociology, those sorts of fields tend to use an alpha of 0.05, whereas the so-called harder sciences like chemistry or biology or physics tend to use the smaller alpha level. They tend to use the 0.01. And we'll talk a little bit why in a future video as well about why you might choose one of these levels over the other. But for our purposes, in our class, we'll be using either the 01 level or the 05, and I will always tell you which one to use. The p-value that we find is going to be like the percentage of the characteristic that we're looking for, kind of, and we're going to be comparing it to that weirdness cutoff. So when we find a p-value, we're going to compare it to the significance level. If the p-value is less than the significance level, that means that the p-value we find is smaller than our cutoff for weird, right? It's less than a 1% chance or less than a 5% chance. In this case, we will conclude to reject the null hypothesis because the results are statistically significant at our alpha level. If the p-value is greater than or equal to alpha, then that is when we will fail to reject the null hypothesis because the results are not statistically significant at the alpha level. The way that I think of statistically significant is like it's weird, right? So if I make a claim about a population, okay, and you go out and you find a sample that is like a counterexample to my claim, right? That would be a weird thing to happen if my claim were true. So that would be a case where your sample is statistically significant. It's super weird according to my claim, so therefore my claim cannot be true. It's unlikely that my original claim was true. That's the case where we would reject that original claim. We would reject the null hypothesis. So let's do some examples. According to bestplaces.net, the mean household income in Utica, New York is about $31,000. Now, Tom wonders whether those who live in Syracuse have a higher mean income than those who live in Utica. So he does this analysis, does a lot of math, and he finds a p-value of 0.041. Let's start by stating Tom's null and alternate hypotheses. Now, in this example, Tom is comparing Syracuse to Utica, and he suspects that there's something different between these two cities. So if you suspect there's something different, then that means that you're fighting a claim that they're the same. So the null hypothesis that Tom is fighting is that the mean income in Syracuse is the same as Utica. In other words, mu equals the $31,048. To form his alternate hypothesis, Tom is suspicious that those who live in Syracuse have a higher mean income than those who live in Utica. Since he suspects the mean income in Syracuse is higher, that means this is going to be a right-tailed test. He suspects that mu is greater than the $31,048. So then he does a bunch of math, and we're going to talk about how to do that in the next video. So there's a bunch of math that gets done, and a p-value of 0.041 ends up being found. So for part B, are the results significant at the 05 level? To determine whether they're significant or not, we need to compare 05 with our p-value of 0.041. A p-value of 0.041 is like 4.1%. Is that less than 5%? Yes. So since the p-value is less than the alpha level, our results are statistically significant. When the results are significant, then you conclude to reject the null hypothesis. Basically, what it means is that your sample is very weird, right? Since our p-value was less than our cutoff of 5%, the p-value is indicating our sample is statistically significant. It's weird if Syracuse and Utica had the same income. Now, Tom could also have conducted this test at the 1% level instead. So instead of using a 5% cutoff, right, less than 5% is weird, Tom could have used the 1%. He could have said, no, my threshold for weirdness is at 1%. If that were the case, 4.1% is more than 1%. So for part C, the results are not significant at the 0.1 level because 4 is not smaller than 1. When that happens, you will fail to reject the null hypothesis at this level. In other words, if I were using the 0.1 level, although the mean income in Utica and Syracuse may be different, it's not different enough to call it like a weird result. Okay? That's essentially what this would be saying. So when you conduct a hypothesis test, you want to make sure that you are choosing your significance level at the beginning. And again, we're going to talk about why you might choose an 0.1 or an 0.5 in a future video. And in terms of our class, I will always give you that information, whether to use the 0.1 or the 0.5. All right, so these are our steps to conducting a hypothesis test. So our first step is to make sure you can do it. So the way that you can conduct a hypothesis test, since it's sort of built off of the central limit theorem, we need to check the central limit theorem kinds of stuff. So we need to make sure that we have a simple random sample. We need to make sure that our sample size is more than 30, or that we know we have a normal population. So step 1 is kind of familiar to us. Steps 2 and 3 are new. So steps 2 and 3 are to state your hypotheses and identify your significance level. Step 4 is collecting information. This is a population mean and standard deviation, a sample size, and your sample mean. And we're going to use formulas to find the usual information. This in particular is going to be a standard error, and we're going to find a z-score. Then we're going to draw a picture shading in our normal curve, and we're going to find a p-value using the standard normal table. So when we found area under a curve before, when we found percent or probability or proportion, we're now going to call that the p-value. So they're basically just the same thing. And then step 8 is a new step. It's to draw your conclusion. This is where you will reject or fail to reject. So I want to highlight that steps 4 through 7 are steps we already know how to do. The math part of the hypothesis test is the same as like a central limit theorem problem, basically. So the math part we already know how to do. We're just going to tack on a few steps at the beginning where we form our hypotheses, and then we're going to tack a step on the end where we now can draw a conclusion from these math steps. That's what we're going to be talking about in the next video. So thanks for watching this introduction to hypothesis tests. In the next video, we'll conduct a two-tailed test. This is going to be a not equals to problem. And then in another future video, we'll talk about a left tail or right tail test as well. Thanks for watching and have a great day.